Good. Let me plug the mouse because now I got a mouse. And what I wanted to do is I wanted to kind of do another last video on the terrain generation because I was just curious. I mean, some of the viewers have, some of the subscribers have basically showed interest in kind of digging a little bit more, a little bit deeper into how does this whole thing work really internally in terms of how is this thing mapped from a from a quantum state perspective and the actual geography of the stuff that's being generated. And so I just wanted to do just dig a little bit deeper into the code, see what we can find. And again, this is Python, and I'm not really super familiar with Python, but it's easy to read. So, and I got a mouse, so I hope that the map that we're going to generate now, maybe we're going to be able to move a bit easier, because before the mouse sensitivity kind of was bringing me some problems, but I think that's because of I'm working on a virtual machine. So, but basically I am within the island generator demo in here, exactly. And there is a there's another tab. So there's another, which is a simplified terrain generator. So Jupyter, can I just open it like this? I don't know. Let's see. Looks like, because this is a simplified one, which I think that what it does, because it's the one that I used first, is this basically generates sort of it has an island as a seed. Because in here, if I take a look at this whole thing, so there's like all the functions in here, and then here you start the interactive part, right? So and let's go these like one by one. So let's first run the whole thing, and then let's try to break it down as we go. So we run the whole thing here, and then so this is how we're going to build this, right? So we're going to first we're going to define a box where we're going to define where do we want the peaks, and then where do we want the valleys. The stages, broad features, mountains, and the sea will go exactly. So, and here, so now this is to choose where you want the low ground to be, under or close to sea level. So this is where the water is going to be. So I'm going to try to make it really exaggerated. So we see that we only want coastline on this side, for example. So I'm going to mark them white like that. Exactly, and then maybe make a sort of a river that goes through or something like that. So we're gonna keep it like this. Okay. Then the next box is for the peaks. So where do we want mountains? No, valleys. So the first is the sea level, right? Peak box. Oh, the other way around. So sorry. So this is the mountains. No. So let's do it again. So first we choose where do we want the mountains to be. So we're going to do basically a landscape where we want the mountains to be all here. And a bit around. Exactly. And we want basically the coast to be kind of here, right? So this is going to be the mountains. Then now, sorry, it just scrolls really bad. Now we're here. Let's run this thing. So now we define where do we want the low ground to be. Why does it have to start with that already? Valley box. Under or close to sea. So first, let's just unclick all these. And what we want is basically we want the sea, so the valley level to be here. I'm not so sure if that's going to all translate into water. but hopefully, and I said that I want kind of sort of a river in between here that goes this way, maybe. Let's see. Let's see what happens. The next step is to actually, okay, plot this, right? So what this does is it takes the peak box. Why just the peak box though? And the valley box. Okay, so and it adds 1 if it's a peak and a 0 if it's not in a 0.5 if it's none of those. And this is still from my previous result, so let's gonna run it again. So that's how it's supposed to look like. Why is this kind of gray? Because I want this to be the actual water, and then the thing in the middle is simply so if I what happens if I do this? Yeah, so that's exactly why is it I want this to be the sea. I'm messing with that probably, but let's see what happens if I put it this way. Exactly, because I want this to be 0, so I want the water in here. Okay. Next, we need to create textures that we want to overlay onto the map. But you see what's happened here. So this is all classical. There's no quantum in here, right? So we're just defining the peaks. We're just defining the geography more or less, and then we need to create the textures. And so I think here's the image you created. Okay, so now I gotta put. Okay, so we need to create the textures that will overlay into the map. To do this, we have made some tools to convert images to quantum states and then back again. This means that we can create a simple image, manipulate it using a quantum computation, and then use the result in our terrain. To start this process, draw a simple image below. Do this by clicking on pixels to switch them between black and white. But how does this map into the textures? So that's the image that I created before. So is the quantumness only happening at the texture level? But how do I tell them that? How do I tell that I want, C or the textures that will overlay onto the map? So that's still not clear what this is doing really. VBox box. So this is just box. Okay. But anyway, so we'll do something like this. I don't know what the clicked ones really mean. So let's see. Here's the image you've created. So now what it does is it goes through the box and it sets that to 1. To 1. Okay. Plot height. Yeah, so that's the image that I've done. Now we'll run it through a quantum interference process. And so this is where now the quantumness comes in. So this basically is turned into a quantum state, which I want to now take a sort of a deeper look in. And give me a second. Gotta check. Gotta check something. Good. So, but if I do, I'm confused. Why is this Z islands? But we've just been. What is going on with ZS then? So this is the image that I've created, and now I go put it through the quantum algorithm that blurs this a little bit, but it's like, what? That's weird. And what if I do this with ZS? Here. Amplitude is square root of height value. Amplitudes are normalized. Here. So that works. So flat height, by the way, if I go and check this out, it's basically, it creates a map. So it creates sort of the seed, which is, it's a flat map. And that's kind of the thing. So I'm gonna go execute that again if I wanna, because otherwise this is taking the Z value. So if I repeat that operation, it's kind of creating more interference. Okay, so as I said, basically you can run it more. So I can run it more. I'll keep it to these. Yeah. This new image will be used as the basis for okay, so this new image will be used as the basis for textures within the landscape. This means that it is good for it to be nicely bumpy rather than have lots of extremes or highs and lows. So run the above process until the result doesn't have lots of pure black. So the quantumness here is not in the Thuringian, it's in the texture being spread in a way that it looks kind of natural. I think I know. And then that's kind of applied. Okay, and then that's applied to random shuffle head, rotate head. What is this? What is that? Create many variants of this basic texture. So we create many variants of this basic texture using the process below. Sample 700. And then now we can get our map. The broad features you supplied will be combined with the many quantum texture patches. The end result will be some nice terrain. Yeah, and that's actually what so that's kind of how we define it, right? So the sea in here, the river getting in, and then the mountains, and then that kind of goes and saves the blocks. We run it, and so ideally now, if I would go and open new tab and say, so we've got now the block CSV here, and then if I remember well, this had to be copied over exactly, copy blocks to these thing because I installed mine test and it just got installed here. So if I copy that and I put my password in, and now I start mine test, and now I basically create a new URL, final test, and create and play game. And okay, there's still mouse issues even despite the fact that I have a mouse. Okay, but it's a bit easier to control. And if I now basically, what was the, how did the thing with the command chat is T, and then it was LB TV, something like that? No, invalid command. How was that? What was that? What was that? What was that? Maybe it's in here. In the simplified, is it explained? LTVV. So LTBV, and that's supposed to load that map. Yeah. Cool. Oh. Why are there torches on the trees? Why are there torches on the trees? What the? Eh? That's funny. Is it part of the texture or? And so if I jump, how is to fly actually? I forgot the commands. Inventory, space jump, climb. Exit sound continue, change keys, exit to menu, change keys. What is the toggle fly K? Okay. K. So I want to fly. We didn't really see if that was that's the map that we've just generated, it looks like. It looks like here you have to see the mountains. There's a flying torch. Interesting. Yeah, I guess blurred already, but so over there should be the sea. Okay, but then this is the, okay, so this is basically what you're doing from a quantum perspective is you're creating those texture patches. That's all you're doing. Okay, I get it. The rest is sort of the traditional way you define the low parts, the top parts, and then so these texture patches, and probably that's why we are seeing some. How can I go down? Oh, just like that. And that's you're probably seeing those torches in there. So if I just dig straight down, get some gold, some caves, going down, 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 down. And I guess probably that just doesn't stop. There's a depth at some point, or I'll just find lava or something. Yeah. Anyway, that's not the point. Is not to play the game, I guess. But um, good. So now let's try to dig a little bit deeper into this. So it's the textures. What's kind of happening, right? So let's die. Die. Yep. Oh, I saved my life. Good. So let's minimize that for a second. So it's really, so what we're doing here is, because I remember that was that for some reason I cannot find here the original Jupyter notebook in the box below, because in that Jupyter notebook it was explained a bit more in detail. But that's sort of the one that we have in here is like a sort of a simplified version, a stripped down version. So tartan. What is a tartan? Okay, a wooden. Okay, crisscross is the okay. Yeah. So the trick is, how are those? So basically, once it's done, we create many variants of this basic texture using the process below. Okay, so we're basically iterating over the sum over each. So we're getting 700 different samples. So we're iterating over that, and then what we're doing is we're shuffling the heights a bit. We're rotating the heights, and then we're pending that. So you're kind of creating random variations of that shuffle height. What does it do? Okay, shuffles a bit. New position. Shuffle grid. Shuffle grid. Okay, just a bit of random. So it just shuffles things around. Shuffle height and then rotate height. What does it do? Rotate height by rotate height Z by angle theta. So what does it do? Okay, so it rotates the height, literally. It rotates that. It moves that around the actual grid. Interesting. Okay. And then that's it. So this is also nothing quantum in here. This is just generating these things. But I'm interested to know how this is being this is being patched together. Islands. This is also for not zero quantum at all. So you get the tartans, which are the textures. You get so you start with a flat height seat, and then you go for each tartan, and so unchosen true, and while it's unchosen, so you pick up a random square in the map, in the grid, right? And then if this random smaller than this, unchosen false. Okay, so it chooses. Key size. Quantum tartans of tartans with the basic map features. So those are the basic map features, right? In this case, ZS. Here's where ZS comes in, right? So this is the, okay. So the ZS is the grid that contains the peaks and the valleys. Okay. And so basically, okay, so it chooses a location that that is valid, right? I guess. And then for XY in tartan, so what is it? What is this doing? It defines x, x, y, y, as in t size. Okay, so it defines the other. Okay, that's I think that I think that what this is doing is it's finding whether that tartan would fit in here, right? Because if you pick a square that is too close to the edge, then the tartan might not fit. I think that's what's happening. So, and basically, if all this happens, then in okay, so for x and y, I see. Okay, so for x and y in tartan, so it traces over all the tartan, then it tries to map it in. The x and y are the coordinates in the actual target map or grid, and then there, it's basically adding that thing in the tartan, right? But adding it, what would adding it do? I mean, normalize the height. Okay. It adds that tartan, right? So what's in the tartan? Good. So now let's take a look at what's in the tartans. Tartans. So tartans. So what's in the what's in the tartans? The tartans are here. Tartans are here. Pend. Round Z. Rotate height. Of grid, yeah. Okay, so it's all basically a grid. Tartan is one of those grids. Okay, quantum tartans. And this is where we're now going to get into the quantum stuff. So this is what you okay. So so you've got a seat, you've got a theta, and then the grid is what you're gonna do. Okay, what you're creating. So basically, you make a grid, and this is what I think this is key to understand the whole thing. It's how is this mapped into a state, because then there's a quantum circuit basically, and all this is doing is creating some interference. So it's basically rotating around the y-axis and then doing a Hadamard gate. So what this is doing is changing the phase, right? So it's literally two gates. This is basically changing the phase, and then with the Hadamard, you kind of create that you're gonna create that either constructive or destructive interference. Exactly. I think that's really it. So where am I? The hate to stay. Let's dive in, because this is really this. If we don't do this operation in here, if we don't do the Hadamard, there's not going to be this interference that basically kind of cancels out things. But this is just a. I mean, I don't know. I can play with this a bit and then see what kind of patterns appear, but I don't think we're going to see a lot of different things. But let's take a look actually. what happens if we don't do the Hadamard, for example, right? Is this the right way to comment stuff in Python, or is it this? So I do this, and now I go back to the part that generates the quantum tartans, which is here. So I'm gonna execute that again, and then just to kind of have a clean seed, because the z is generated out of these, and then yeah. Okay, so you see, okay, cool. So instead of interference, the whole thing has just been rotated. So that's why kind of you see it displaced, I think. If I keep doing that, yeah, it comes back, because it comes back to the original state, because it's reversible, right? Cool. Okay, so this is the. But I'm curious, what else can you? I mean, I don't know what else could you do in here. This scrolling is so bad. Where tartans here. Scrolling is so bad. I was curious if it would just do an RZ, for example, right? Would run that, and then I would go basically, how is the. Just want to check what's the battery status of my laptop. Okay, should probably get down with this quickly. So basically, if I go back here and I do that again, and now I do this again, and now I create a quantum tartans. Interesting. It's a completely different. And what if I do it again? Oh yeah, well, sorry, I kept the. I should have removed the Hadamard just to appreciate the difference in terms of rotation or whatever. So I want to do that again, and now that again. Nothing happens, of course, because interesting, because probably the state is just a bunch of zeros and ones, right? So that's why just a z rotation changes nothing really. Interesting. Yeah, so it kind of makes sense. You see how this? Okay, so I think I hope that's kind of enough to satisfy your curiosity. Definitely, you could play with different circuits and see what kind of patterns of interference arise. I was just want to take a look at this quickly before I go. Hide the state converts a high map into a quantum state. So how does it do this actually? So state. Okay, so it's the length of the grid, and then for each. So for each position in Z, and again, what is Z? Z is, in this case, the seed. And then, okay, so the seed is the, okay, so the seed is then the image that I created, that I'm creating. Then grid is and grid is the actual grid. And so what it does is, for each position in the seed, the state is the square root of the height value. And then, of course, you've got to normalize the amplitudes. So they all add up to, so the squares add up to 1. Converts the height map. So basically what this is saying is that Okay, so for each, but that's a pretty big. But how big is the grid? I mean, because what? So each square is an actual state, and then the height is it's basically the probability. That's what it seems to say. That's the length of the grid. So you define a state that it's as the state is as big as that, so, and then and each possible outcome in there. So 0, 0, 0. So if this is if it's like a 10 per 10, right, you would have like 100 possible states, and then so 100 possible combinations, and then each of them, the height is the actual amplitude in there. So but you just normalize it, so it is an actual valid quantum state. Yeah, okay, but it's not that. So yeah, but still you don't need so many qubits in this case, right? Because having like I mean, really, you can actually, if you say what's 2 to the power of like, even if you say that your system is just 16 qubits, right? This means you've got this amount of stuff, this amount of squares in the grid, which, of course, if you divide it by 2, right, you get like, so it's 32,000 squares wide and long. So it's like 32,000 squares per 32,000 squares. So it's a pretty good, it's a pretty big grid. Anyway, so but you see, right? So the idea here is the quantum stuff here is coming into play when you generate the actual textures, exactly, the actual textures, which are then combined. Which then, with a quantum, sort of a simple quantum circuit, we are creating interference and we're blurring them so they look a bit more, kind of really random, right? I think that's the key of this, is the randomness. That's real randomness. I mean, not if you're running a simulator, but it's real randomness. And then you actually apply a classical algorithm to create 700 variations of that. So you're not applying the same thing over and over again. And then you just merge them with your height and your valleys and your peaks kind of feature maps. And I guess that and I guess that defines, because what does, for example, that's what I wanted. So okay, so this is the key. It's like that's what I. So what defines whether it's water or sand or dirt or whatever, it's basically this big if else. Grass with trees. If it's smaller than terrain 1, it's smaller than terrain 2. What is terrain? So okay, height to image. So terrain 1, terrain 2. Yeah, but where's, for example, terrain 1 defined, right? If terrain. Height to image. Where is that used? Terrain. So that's the terrain. Okay, so that literally defines. Okay, so actually, that's kind of weird because that really then defines what is grass and what is grass with trees and what is stuff like that, right? So, and actually, because I was thinking like all that this really does, the texture part is just add something on top of your features. So it really um, adds a bit of extra hate, right? I mean, that's what I would say. And then at the end of the day, that doesn't really define the texture directly. It's not you're painting and saying, here I want to be the trees and here I want to be the grass. But I mean, you get the point. So the real thing here is you're adding a bit of randomness. There's no quantumness that defines really the actual characteristics of the map. And probably in my previous videos, I was just going to fast through all these, but that's really what this looks like. So the quantumness in here is in kind of adding this little randomness that is real randomness because it comes from a real quantum computer if you run it against an actual machine, and that just makes it more appealing, I guess. Cool. I hope that's good, and it's good enough. We're going to park that project already. I think that's. But it's a nice showcase. Cool. So, and now we'll just